All right. Hello. Howdy. How's it going? So, I know with split classes and all, it's been frustrating with you reading through PowerPoints when you're not in my class and then not really understanding what the PowerPoints are saying or not getting an explanation from me or being able to listen to my explanations or me being able to directly answer questions. I know that's been frustrating and annoying and probably not the best way. Definitely not the best way for you guys to be learning material. So, because we are in split classes, sadly, you will still be learning stuff when you're not in my class just because I want to be able to do labs and whatnot. But now we're going to have these fun, super spectacular videos or recordings of me going over a PowerPoint, going through the PowerPoint. So when you're out of class, you get an explanation from me. And then when you come into class, I can still answer questions before getting into activities. In a dream world, we wouldn't be split. COVID wouldn't be an issue. We could see each other's noses and nostrils, and then I could teach you this stuff in person every single day, and we can still have time for labs and activities. But the cards were given to me. We're going to deal with the deck, if that's the saying. We're still going to learn stuff outside of class, but now you're going to have awkward videos of me that you're going to be watching. Explaining some stuff so you have a better explanation. So when you do come into class and we do activities and labs, you're not like, Mr. Peterson, I'm freaking lost, because that's no fun for everyone. So these videos from now on, you'll probably get an awkward blurb introduction, me speaking, and then I'll hop into the PowerPoints. On the downside, you have to watch awkward videos of me. On the bright side, you get amazing jokes because when you read the PowerPoints, the delivery of my amazing jokes is not there. But now, because I'm here, this video, you'll get those jokes. So the class that I was in here doing the electron experiment on Monday, we'll be watching this on Tuesday, just to clear that air. We're working on electron configuration. This entire unit is on electrons and periodic trends. Periodic trends will have its own video. This video is on electrons and electron configuration. What the heck is electron configuration? What are electrons? Which I hope you guys know by now. And if you don't, then I'm really sucking at my job. But electrons, electron configuration will be this video, and then we'll have a separate video for periodic trends. So I'm going to share my screen into hopefully what I think is the right PowerPoint. Yes, all right. And you'll be able to see me awkwardly up in the corner. Electron configuration is what we are looking at this unit. To start with, we have this. We have the Bohr model. We've talked about the Bohr model already. The Bohr model is just a way to show what an atom looks like. As you can tell on here, you have these neutrons, and hopefully you guys can see my mouse. You have these neutrons in red and protons in blue that take up the nucleus. So the nucleus is made up of protons and neutrons. Electrons, here's my nucleus, electrons are going to be scattered around this nucleus. What Bohr is saying and what this model is saying is we have specific electron orbits where electrons fall around a nucleus. There are given spaces where electrons will be. As you see here, electrons will always be in this particular area and always be in this particular area. That is Bohr's model. We now know that obviously you can't say the exact spot they're in because it's a probability, and it's depending on the amount of energy in an atom and many other things that we'll talk about. So we know that the Bohr model isn't completely accurate in terms of the realistic presentation of an atom. For electron configuration, Bohr model is what we use because it shows energy levels in particular places of where an electron falls. So this Bohr model shows that protons and neutrons are in the center, and electrons are in particular specified areas around it. Ha, see, our joke that you guys get. Ha, one day a proton and neutron walked down the street. Then the proton said, I dropped an electron. And whoever wrote this joke spelled electron wrong, so that's embarrassing. But he then said, help me look for it. The neutron replied, are you sure? And then the proton replied, I'm positive. Get it? Because protons are positive. I'm positive. That's a good one. All right. So we'll skip back. Bohr's model: protons, neutrons in the nucleus, electrons in predisposed areas around the nucleus. This is a little bit fancier version where we have our nucleus and then we have our pre-specified areas where my electrons will fall. In this case, these are labeled n equals 1, n equals 2, and n equals 3. N just relates to the energy level, where exactly an electron will fall. N1, n equals 1 is the closest to the nucleus, and then n2, n3, so on and so forth. These energy levels dictate where an electron wants to be as you fill in what you'll see is the electron configuration. Electrons want to be closest to the nucleus. Electrons are negatively charged, the nucleus is positively charged, opposites attract, so they want to be closer to the positively charged things. Here's my negative charge, here's my positive charge, they're attracted to the nucleus. So they want to fill the lower energy levels first. Energy levels are just a way of saying location of an electron. N equals 1 is the lowest energy level, and then 2, 3, 4, 5, so on and so forth. So electrons want to fill n equals 1 first. If n equals 1 is full, then you go to 2n. If 2n is full, then you go to 3n, excuse me. But you always want to be closest to the nucleus as possible. If a spot's open in 1n, you're going to take that 1n spot before going to 2n. So if here's my nucleus, you always want to fill 1n before going and filling 2n. Mainly because the lower energy that there is, the happier an electron is. So lower energy, happier. So you want to fill 1n before going to 2n because it's more favorable for the electron. It wants to be closer to this positive charge nucleus because opposites attract. That's my electron and nucleus. So we said this energy level or shell is 1n, 2n, 3n. So we have our nucleus, our first energy level, our second energy level, and our third energy level. Each energy level or shell is once again a fancy way of saying the location of an electron. Each shell has a particular or a specific number of electrons it can hold. In this case, the first shell, or the one closest to the nucleus, can hold 2 electrons. The second shell can hold 8 electrons, and the third shell can hold 18 electrons. So here's my nucleus. 2 electrons want to be in the first shell, but once 2 electrons are in the first shell, it's completely full, so you need to go to the second shell. 8 electrons can be in the second shell before going on to that third shell. So like I said, electrons always want to be closest to the nucleus as possible. So you're always going to fill the first shell before going on to the second shell. This first shell is 1n, this second shell is 2n, and this third shell is 3n. 1n can hold 2 electrons, 2n can hold 8 electrons, and 3n can hold 18 electrons. So then we get into this diagram where you're like, what the hell is this? Well, perfect, because I'm going to talk about it after I drink some water. So this is your electron configuration. This is just a fancy way of describing the first shell, the second shell, and the third shell. It's written as increasing energy, so the top is the lowest energy, and an increasing energy as you go downwards. So you get these things of 1s2, 2s2, 2p6, 3s2. What is that? So we'll take 1s2. You look at 1s2 and you break that into 3 different parts. Your 1 is the energy level. So this 1 is the energy level, where it is in relation to the nucleus. That's 1n. That's the first shell. So you know that's the first position after the nucleus, first position. Your s relates to the orbital. So what portion of the energy level is it in? And then your 2 up here relates to the number of electrons that are in that specific orbital. So 1s2 just says 1 being closest to the nucleus, s being the position around the nucleus, and 2 being that there are 2 electrons in the s orbital in the first energy level. So you'll see if you follow these arrows, 1s2 is first, and then once 1s2 is full, you go to the second energy level. You see the second energy level is comprised of 2s2 and 2p6. That's because if we remember, the second energy level can hold 8 electrons, right? So we have 2 electrons that can be held in the first energy level, and then 8 electrons that can be held in the second energy level. S is an orbital that can hold only 2 electrons, and P is an orbital that can hold 6 electrons, or 6, sorry, I'm used to ASL, so I say 6 this way. But 6 electrons in the P. And you'll see that as you fill in the lowest energy level first, you then go up to the next highest, 2, you fill up 2 fully, and then you fill up 3 fully, and then you go on to 4, and so on and so forth. You start with 1, energy level of 1 because it's the closest to the nucleus, and then you build outwards with a specified number of electrons in each energy level and in each orbital. As you see with these superscripts, the s orbital can hold 2 electrons maximum, the p orbital can hold 6 electrons maximum, and the d orbital can hold 10 electrons maximum. There's more orbitals out there. There's f orbitals, each with different shapes. For this class, you need to know s can hold 2, p can hold 6, and d can hold 10. Oh, electron configuration? How boring. Get it? Because this spelling of boring is like Bohr, the Bohr model. So how boring. But clearly we know it's not boring. But this is just a funny joke. Nice. So we talked about S, we talked about P, and we talked about D, and we talked about F. S, P, D, F. This is just a model of the periodic table. You see that the first 2 groups, group 1 and group 2, are comprised of s orbitals. These are metals, or your transition metals, or groups 3 to 12, are the d orbitals. And then your metalloids and nonmetals, halogens, and noble gases are p orbitals. 1s, that's helium, that's also over here. So you fill in, it's like reading a book, left to right, top to bottom. And I was going to hold up a pen to the periodic table, but you can't see that, so that's super awkward. So hopefully you can see my mouse. But you start in the top left, and then you go left to right, and then top down. So for example, hydrogen is 1s, helium's 1s2, lithium's 1s, 1s2, 2s1, and so on and so forth. We'll get into examples. I just want you to know that groups 1 and 2 right here are S, metalloids, halogens, and noble gases are P, and then transition metals are D orbitals. So we get into this idea. Once again, I just want to keep reiterating it because I know prior to me doing this video, nothing makes sense, or not much makes sense because you don't get an explanation. So I want to make sure my explanations are thorough. You have your nucleus. It's the easiest to fill 1s. The closer to the nucleus, the less energy associated with it because it's happy to be there. Positive nucleus, electrons are happy to be right by it because that's positives, negatives, opposites attract. As you get further away from the nucleus, the overall energy associated with that position increases. That's just because you're around fewer positive things because you're further from the nucleus, and around more negative things because there's more electrons surrounding you. So you get a greater amount of repulsion or a greater amount of energy present. So You want to fill the lower energies before going to the higher energies. Lower energies are closer to the nucleus. Higher energies are slowly further and further away from the nucleus. So there are 3 rules that I'm going to run through right now associated with electron configuration. The first one is the Aufbau principle. This states that electrons are simply lazy. Electrons want to occupy the lowest energy levels that are available. So if 1s is available, those electrons are taking it ASAP. If 1s is full, but 2s is available, it's taking 2s. So the lower energy levels that are available, the electrons want to be there. The second rule is Hund's rule. That states that electrons are unfriendly. They don't want to share orbitals unless they have to. Remember, electrons are negatively charged, so electrons don't want to be close to each other. Opposites attract, similarities repel. So if electrons don't need to be near each other, they will not. So you look at this, we have 1s2, 2s2, and 2p3. This is just the orbital method, orbital diagram of electron configuration. What this is saying is 1s2, where these arrows represent electrons, 2s2, where these arrows represent electrons, and then 2p3. You see that there's a right method and a wrong method. This wrong method is wrong because it's 1s2, 2s2, and 2p3, where you have 2 electrons sharing this orbital when there's a third orbital present. That's incorrect. No bueno. We don't like it. Electrons are negative, 2 electrons, both negative, repel. So if there's an available empty space, electrons will fill it. Hence why this methodology, this writing of it is correct. Because electrons are not filling orbitals because they don't have to. If this was 2p4, or 4 electrons, you would then have another electron written in right here, because while it doesn't want to share an orbital, if it can have an orbital at lower energy, it will share before moving up an energy level. So the Hun rule says, it's still a rule, it says that electrons will not share an orbital or will not be drawn in next to another electron unless it has to. And then our third rule is our Pauli exclusion principle, which states that only 2 electrons can fill a singular orbital. 1s can only have 2 electrons. 2p can have a total of 6 electrons, where each orbital, or each one of these dashed lines, as there's 3 different dashed lines, can hold 2 electrons. So 2p can hold 6 electrons, where each orbital within 2p can hold 2. So you can't draw all 6 on one dashed line. You need to have 3 different dashed lines when you're working with the p orbital. All right. Electron configuration. 2 ways of writing it. The first way is electron configuration, written with the letters and numbers. 1s2, 2s2, 2p6. And then the orbital diagram is written with the boxes and arrows. Or if my computer works and we go back, these arrows written like this is the orbital diagram. So what the heck does this mean? If we look at an example, lithium. Lithium, drawn in, has 3 electrons. 2 electrons maximum can fill the first energy level, and then 1 fills the third. So you have lithium written as an electron configuration, 1s2, 2s1. Then in orbital diagram, you have boxes and arrows in which this box represents 1s2 and this box represents 2s1. Aluminium, aluminum, aluminium, British, European, whatever works for you. Aluminum has, hello, I'm doing a video right now, so maybe you can, you can awkwardly.
It's not for me.
Oh.
I was just going to ask for help.
Yes, I'm doing a video for you guys. You can, yeah, you can. They're just gonna see this now when they're watching my video, and so that's totally okay. Sure,
my chemistry class.
Now I had to put my mask. All right, so you guys are more than happy to be in here, and then when I finish this, I can help you out. So now this is gonna this is gonna be.
This is just getting more and more awkward.
I mean, my nail polish is pretty sweet, but now that this video is just gonna be incredibly awkward. But you know, that's okay. That's all right. Okay. Don't look at me. Face that way, because if you guys are staring at me, my face is gonna be bright red, and I'm gonna be laughing the entire time. So just stare out the window and watch the snow. Oh my god. Okay. Oh my god. All right. Electron configuration and orbital diagram for aluminum. If you count it, it has a total of 13 electrons. Like I said, the first energy level can have a total of 2 electrons. So once 2 electrons are in the first energy level, then you go to the second energy level. The second energy level can hold 8 electrons. So once that's filled, you have to go to the third energy level. That can hold a maximum of 18 electrons, but in this case, we only need to fill in 3. So you have the first energy level with 2, the second energy level with 8, and the third energy level with 3. That being written as the first energy level, 1s2, the second energy level, 2s2, 2p6, and then the third energy level with 3 electrons being written as 3s2, 3p1. Remember, s orbitals can only hold 2 electrons, so once s is filled, bye guys, have fun. Once the s orbital is filled with 2 electrons, then you go forth to fill the p. So this is the electron configuration for, and of course that, there, I'll move the bar to the top. You get 1s2, 2s2, 2p6, 3s2, and 3p1. That is the overall format of electron configuration. You then take this electron configuration and move it to the orbital diagram with arrows, where you have 1s2, excuse me, at the lowest energy level, and then increase energy to 2s2, 2p6, where you have 2 electrons in each orbital, so 2p6, 3s2, and then 3p1. So we again get into the writing of configurations for ions. The end goal for any particular element is to have a full s and a full p orbital. Elements want 8 valence electrons to become fully stable, so elements will either gain or they will lose electrons to become stable. So they want 8, so they will either lose 8. What's up, Kian? I'm just doing a video, but if you want to come in here, you can do work if you want. Yeah, that's totally fine, man. Cool. All right, I'll see you tonight, bud. Jeez, I am popular today. Right, Bree? Bree's awkwardly just... Bree, say hi to class. Bree, say hi. Well, you know what? I've gotten so many distractions that you guys, you probably still watch this. That's Bree's back here, guys. All right. Bree, I'm almost done. Elements want 8 valence electrons to become fully stable, so they will either gain or lose electrons to become stable. Like I said, they want a full s and p orbital, so they want a full s2 and p6 to be ideally the most stable and most comfortable version of themselves. Periodic table. It's super easy to figure out how many valence electrons each group has. Group 1 has 2, Group 1 has 1, Group 2 has 2, Group 13 has 3, Group 14 has 4, and so on and so forth. You want noble gas configuration. You want 8. So what you'll see is 5, 6, and 7 elements with 5, 6, or 7 valence electrons want to gain 3, 2, or 1 valence electron to become 8. Elements with 1, 2, or 3 valence electrons want to throw away. They want to give away valence electrons to get 8, because it's easier to throw away 2 than to gain 6. Remember, we want to look at favorability with energy and whatnot. So we take a look at sodium. Sodium is 1s2, 2s2, 2p6, 3s1. Sodium has 11 electrons. 1s2, 2 electrons in the first energy level, 8 electrons in the second energy level, and 1 electron in the third energy level. That's not very stable. It doesn't have a full s and p orbital. and only a full s&p orbital. This 3s1, this one extra valence electron is screwing over its feng shui. Is feng shui a word, Bree? Feng shui is a word. The vibe, feng shui. Neon, however, has 10 valence electrons if you look at the periodic table. 1s2, 2s2, 2p6. Neon's content. Neon's stable as could be. So sodium, its end goal is to lose this electron in 3s in the third energy level to become like neon. So it loses it. You then write a positive charge next to it because it's lost. It now has more protons than electrons, and then you would write it as 1s2, 2s2, 2p6. It's stable. It's content. Same thing with chlorine. If we take a look at chlorine, chlorine's electron configuration is written as 1s2, 2s2, 2p6, 3s2, 3p5. It's not stable. That 3p5 is killing its vibe. It wants a full s and a full p orbital to be happy. If you take a look at argon, which has 18 electrons in comparison to these 17, it's 1s2, 2s2, 2p6, 3s1, 3s2, excuse me, 3p6. That's written wrong. My apologies. That's content. So chlorine's goal is to gain a singular electron to become stable. Gaining an electron will put it over at 18 electrons in comparison to 17 protons, making it stable. So this ion configuration would be Cl minus, written as 18 electron configuration. And we'll get more practice with that. The last thing I'm going to mention, and I know I've been blabbering for a bit, so bear with me. The last thing I'm going to mention is how exactly do we figure out if an electron gains energy or loses energy? So like I said, we have energy levels, energy level 1, 2, and 3, where each energy level has a particular amount of energy associated with it. If an electron goes up an energy level, it absorbs energy. It needs to take in energy to be able to go up from a low energy to a high energy. So if I go from N1 to N2, it's taking in energy. All right, electrons absorb photons or energy, base units of light, to gain an energy level. Likewise, if I'm going down an energy level of 3 to 2, your electrons will give off energy or give off photons, release energy to be able to move down. So electrons jump up an energy level, it'll gain energy, and when electrons go down in energy, it will release energy. This energy being released from an electron decreasing in energy levels, it can be calculated with a series of calculations. Photons, right here, this is important to note, are base units of light. So we can visibly see an energy change if energy is being released from going from an energy level of n equals 3 to n equals 2. Photons or base elements or base units, of light will be released, and we can see that light that's being released. That's where we get into this fun jazz. We have some equations that will be able to allow us to calculate and determine how much energy is being released. The first one is C equals lambda V, or C being the speed of light equals wavelength times frequency. Light behaves as a wave, electrons have wave tendencies. So you'll always have a frequency and wavelength associated with a certain amount of electrons and photons. C is always a constant. C is always the speed of light at 3 times 10 to the 8th meters per second. Colors are also associated with each wavelength. All right. So like a wavelength of 700 nanometers is around red, a wavelength around 600 nanometers is yellow. So you always have an associated wavelength with a color. So if I know C always being constant and a wavelength that I can get from a color that I see, I can calculate the frequency. Or frequency is just speed of light divided by wavelength. So then I have frequency. Then using this equation that directly relates to each other, I can figure out my energy because I already have frequency that I just calculated from this equation, and h, which is Planck's constant, which is a given, I can figure out my energy associated with something. So you then get into problems like this. Find the energy of a red photon with a frequency of 4.57 times 10 to the 14th hertz. Well, I need to find energy. I know h, that's a constant. I know my frequency because I gave you the frequency. So it's just plug and chug to say that something of red light, a red photon, will be 3.03 times 10 to the 19th joules. That's how much energy is associated with a red photon. Another type of question is an electron in a hydrogen atom dropped from the 5th to the 2nd energy level, and 4.58 times 10 to the negative 19th joules of energy is released. What's the frequency? Well, if I know how much energy is released, and I know Planck's constant, I can figure out the frequency. And then given the frequency, I can figure out the wavelength. So I know what type of color is involved with an energy drop from the 5th to the 2nd energy level. So if I go back here, the people watching this will or maybe not have done the flame lab yet. When you light different chemicals on fire, or you hold it over a flame, you get a different color produced. That's just the energy being released of that compound, and you get different colors because each compound has a different amount of energy being stored in it. That's why you get, maybe if I light some, like for example, lithium chloride, if I hold that by a flame, pink light is given off because it has around a certain amount of energy that correlates to a wavelength around 450 nanometers. All right. We will get more practice with all of this. This is just an introductory video to kind of get you familiar with electron configuration and energies associated with electrons. In class, when I have you next, we will be going over more of this to get a better understanding. But like I said, I'm going to start doing these videos because I think it helps a lot more than just reading a PowerPoint without my 2 cents. So I hope you enjoyed.